Everything that the models were telling us 3 weeks ago about this August has turned out to be wrong. Not slightly off, not within the normal margin of forecast error that meteorologists account for and communicate to the public as uncertainty ranges. Wrong in the fundamental sense. Wrong about the direction, wrong about the magnitude, wrong about the timing, wrong in ways that matter to every person in the southern and western United States who is planning their life, their business, their crops, their water management decisions around what the August forecast was showing. The forecast has collapsed. The atmospheric pattern that the models projected for this month, a pattern that would have delivered relief from the heat across Texas, meaningful precipitation to the parched Southwest, a moderation of the extreme conditions that have defined this summer, that pattern did not materialize. What has materialized instead is something that the models consistently failed to capture, something that the numerical forecasting systems that meteorologists rely on have been struggling to represent accurately, something that real people in California, Texas, and across the South are feeling in the most direct and physical way possible. The heat that was supposed to break has not broken. The rain that was supposed to come has not come. The relief that was forecast has not arrived. And now the question that matters, the only question that matters, is what actually happens next. To understand why the forecast collapsed and to have any confidence in what comes next, you need to understand something about how weather forecasting works and where its limits lie. Modern numerical weather prediction is an extraordinary scientific achievement. The models that meteorologists rely on, the American GFS model, the European ECM-WF model, the Canadian GEM model, the ensemble systems that run dozens of slightly different versions of the atmosphere simultaneously to capture uncertainty, represent some of the most complex and computationally intensive simulations that human civilization produces. They assimilate millions of observations from satellites, from weather balloons, from surface stations, from aircraft, from ocean buoys, every 6 hours. They solve the equations of fluid dynamics on a planetary scale at spatial resolutions measured in kilometers. They have transformed weather forecasting over the past 50 years from an art based primarily on pattern recognition and experience into a science capable of producing skillful forecasts at ranges that would have seemed impossible to the meteorologists of previous generations. But the models have a specific and well-documented weakness, and it is a weakness that becomes critically important in exactly the kind of atmospheric situation that is unfolding right now across the United States. That weakness is in representing and predicting blocking patterns. The persistent, self-sustaining ridges of high pressure that lock weather into place, that resist the normal tendency of the atmosphere toward change, that maintain themselves against the efforts of incoming disturbances to break them down. These are the atmospheric features that numerical weather prediction models have historically struggled most to forecast with accuracy. The models tend to underestimate the strength of blocking. They tend to predict the breakdown of ridges before those ridges actually break. They tend to suggest pattern changes that are actually several weeks away, presenting them as imminent in a way that generates forecast expectations that then fail to verify. This is what has happened to the August forecast. The models, 3 weeks ago, were showing signals of a pattern change, a weakening of the western ridge, a breakdown of the blocking configuration, a southward dip of the jet stream that would deliver fronts and moisture into the heat-stricken regions of the southern United States. Meteorologists communicated those signals to the public as possibilities, appropriately hedged in the language of forecast uncertainty. But the signals were strong enough, and the models were consistent enough, that the expectation of pattern change became embedded in the public consciousness and in the planning of everyone from water managers to farmers to emergency planners to the ordinary people who check the extended forecast and decide based on what they see how to manage the weeks ahead. And then the ridge did not break. The blocking pattern strengthened rather than weakened. The jet stream that was supposed to dip south stayed far to the north. The fronts that were supposed to push into Texas and the southwest were deflected or dissolved, and the August that was forecast, the August with its promised moderation and its expected relief, was replaced by the August that is actually happening, which is not moderation at all. It is intensification. It is a heat pattern that is digging deeper, locking harder, sustaining itself with a persistence that has made a mockery of the forecast confidence that was communicated based on what the models were showing. Why did the models fail? This is not a rhetorical question. It has a specific technical answer that is important to understand because it shapes how much confidence we should have in what the models are now showing for the weeks ahead. And it reveals something fundamental about the limits of current forecasting technology when faced with the kind of atmospheric pattern that is dominating the summer of 2026. The models failed because they underestimated the strength and the self-sustaining character of the soil moisture feedback that was operating beneath the heat dome. We have discussed this feedback in other contexts, but its role in the forecast failure deserves explicit attention here. As the heat dome persisted through July and into August, the soil beneath it dried out progressively. That drying drove the soil moisture feedback, the process by which a drying, warming land surface removes the evaporative cooling that would otherwise moderate temperatures, and in doing so provides additional heat energy to the atmosphere above it that reinforces and strengthens the ridge. The models were not adequately representing this feedback in real time. Their soil moisture states were running too wet relative to what was actually happening on the ground, because the observations that feed the model's soil moisture analysis were not capturing the full extent of the drying that was occurring across the region. The consequence of that model error was systematic and compounding. Because the models thought the soil was wetter than it actually was, they also thought the land surface was cooler than it actually was. Because they thought the land surface was cooler, they were underestimating the sensible heat flux into the atmosphere, the direct warming of the air from the hot ground that was strengthening the ridge. Because they were underestimating the ridge's strength, they were overestimating the likelihood that incoming disturbances could penetrate it and break the pattern. Because they were overestimating the pattern change probability, they were generating the false dawn of an August relief that was never actually going to materialize, given the true state of the land surface beneath the heat dome. This is the technical story behind the forecast collapse. But the human story is what matters most, and the human story is about the decisions that were made or not made based on the forecast that turned out to be wrong. The rancher in West Texas who held off on hauling water to his stock tanks because the rain was supposedly coming in 2 weeks. The water district manager, who did not activate conservation measures as aggressively as the situation warranted because the extended forecast suggested relief was on the way. The public health official who scaled back heat emergency operations because the forecast showed temperatures moderating by mid-month. The farmer who decided not to irrigate as heavily because the models were showing precipitation in the extended range. All of these decisions, made in good faith based on the best available forecast information, have now been overtaken by a reality that the forecast failed to predict. The consequences of those decisions are being paid right now in heat stress, in depleted water supplies, in damaged crops, in public health emergencies that are more severe than they needed to be if the forecast had been accurate. This is not a condemnation of the forecasters or the models. It is an honest accounting of what forecast failure means in the real world, where decisions made on the basis of forecast information have consequences that unfold regardless of whether the forecast verifies. And it is an argument for the kind of conservative worst-case planning approach that weather-sensitive decision-makers are sometimes reluctant to adopt because it costs resources and generates alarm in situations where the event does not ultimately materialize. The cost of preparing for a heat event that does not fully develop is always lower than the cost of failing to prepare for one that does. The August forecast collapse is a reminder of that truth in the most concrete possible terms. Now, let us talk about what actually happens next, because this is where the analysis becomes most important and most difficult and most necessary. What happens next is shaped by two competing forces. The first is the continued strength of the blocking pattern that has produced everything we have described. The locked heat dome, the suppressed moisture, the failed frontal passages, the parched and heating landscape. That pattern is not going away quickly. The soil moisture feedback that helps sustain it is still operating. The ridge is still strong. The jet stream is still displaced far to the north. In the immediate near term, meaning the next 1 to 2 weeks, the dominant expectation, calibrated by the lesson of the forecast collapse, must be for a continuation of conditions broadly similar to what we have been experiencing. Not necessarily more extreme than the current situation, but not the dramatic relief that previous forecasts suggested either. More of the same, with the same accumulating consequences for water, agriculture, energy, and human health. The second force is the slow but real evolution of the seasonal cycle and the background climate pattern. August is not July. The sun angle is changing. The days are shortening. The energy input from solar radiation that drives and sustains the heat dome is beginning, ever so slowly, to decline as the northern hemisphere moves away from the summer solstice. These changes are gradual. They will not produce a sudden dramatic shift in the pattern. But they are real and they matter because they are continuously, if slowly, eroding the atmospheric conditions that have maintained the ridge. At some point, and the model suggests this is more likely in the back half of August than the front half, though the forecast collapse counsels humility about any specific timeline, the seasonal evolution will tip the balance and the pattern will begin to change. When it changes, the change is likely to be significant rather than gradual. Blocking patterns in the atmosphere do not typically weaken slowly and uniformly. They tend to maintain themselves stubbornly until some threshold is crossed, and then they collapse relatively quickly as the circulation reorganizes around the new configuration. The transition from a locked, blocked pattern to a more progressive, mobile pattern can happen over the course of a week or less, and when it does, the weather changes that come with it can be dramatic. The moisture that has been blocked from reaching Texas and the southwest can surge in rapidly once the ridge moves. The fronts that have been piling up far to the north can plunge south in rapid succession. The temperature drops that were forecast weeks ago and failed to materialize can arrive with a sudden intensity that catches people off guard in the other direction, from heat emergency to flash flood watch in a matter of days. This is the pattern transition dynamic that people in the affected regions need to be prepared for, because it is as consequential as the heat event itself. When the blocked pattern finally breaks, and it will break, the only question is when, the atmosphere does not simply return to normal. It overshoots. It delivers the moisture and the frontal passages that have been held back, concentrated into a shorter time period than they would have been in a normal progressive atmospheric pattern. The rainfall that comes when the ridge breaks will come quickly and intensely to soils that have been baked dry, soils that have lost their infiltration capacity, soils whose surface crusting and cracking will cause even moderate rainfall to run off rather than soak in. Flash flooding risk, ironically, is highest in the period immediately following an intense heat and drought event, precisely because the land surface is least able to absorb rainfall at that moment. Texas knows this dynamic. The hill country in particular has experienced the brutal juxtaposition of extreme drought, followed by catastrophic flooding in the same year more times than anyone who loves that landscape would wish. The Llano and Pedernales and Blanco rivers do not care that their watersheds were dust bowls a month earlier, when a slow-moving thunderstorm complex stalls over the headwaters and drops 10 inches of rain in 3 hours. They rise with the same murderous speed regardless of the antecedent conditions. And in fact, they may rise faster because the drought-hardened soil refuses to absorb the water that the flood-hardened observer might expect the ground to soak up after so much dryness. California faces the same dynamic in its own seasonal context. The atmospheric rivers that a pattern transition in late August and September can deliver to California arrive on landscapes that have been baked and dried by months of heat, on hillsides that may have burned in summer wildfires, on watersheds whose soil moisture is at its annual minimum. The debris flows that result from intense rainfall on burn scars have been among the most lethal and destructive weather events in California's recent history, and they occur not during the fire season itself, but in the weeks and months after fires, when winter or late-season precipitation falls on the compromised vegetation-free terrain that the fires left behind. The Southwest more broadly, Arizona, New Mexico, southern Utah, and Colorado, faces its own version of the pattern transition risk. The monsoon circulation that normally delivers the region's summer rainfall in July and August has been suppressed by the same ridge that has been locking heat over Texas. Monsoon moisture that should have reached the Southwest has been deflected or weakened. When the ridge breaks and the monsoon circulation reestablishes itself, the moisture that has been building over the Gulf of California and the eastern Pacific can surge northward with unusual intensity, delivering the accumulated moisture debt of the suppressed monsoon in a compressed time frame that increases the flood risk across the already drought-stressed landscape. The Gulf Coast and the Southeast face a specific version of what happens next that involves the interaction between the collapsing August forecast and the active hurricane season that is building in the background. As the blocking pattern that has dominated the atmospheric circulation begins to evolve, the steering currents that control the tracks of tropical systems in the Gulf and the Caribbean will change. Systems that might have tracked northward into the Gulf under the previous pattern may track differently under the new configuration. The window of vulnerability for the Gulf Coast states shifts as the circulation reorganizes, and the specific threats that the active tropical season presents may align differently with populated areas of the coast, depending on exactly how and when the pattern transition occurs. None of this is knowable with precision at this point. The forecast collapse has demonstrated definitively that the model's precision in predicting the timing and character of pattern transitions is limited. What can be said with confidence is that the transition will come, that when it comes it will be significant, and that the weather on the other side of it will be as different from the locked heat of the current pattern as it is possible for August and September weather to be in these regions. Not simply moderation, but the energetic, moisture-laden, flood-risk-elevated, severe weather possible pattern that characterizes the atmosphere when it is releasing stored energy and reorganizing itself after a prolonged blocking event. The lesson of the collapsed August forecast is not that forecasting is useless. It is that forecasting has specific, known limitations that should inform how forecast information is used in decision-making. When the models are showing a pattern that requires a blocked, self-sustaining ridge to break down on a specific timeline, the appropriate response is not to plan around that timeline as a certainty. It is to plan around the range of possible timelines, to make decisions that are robust to both earlier and later pattern transitions, and to maintain the vigilance and the resource positioning that the current extreme conditions demand, regardless of what the extended forecast is showing. What actually happens next in California, Texas, the Gulf Coast, and the South will be written by the atmosphere on its own schedule. not on the schedule that the model suggested, but the direction is clear. The heat will eventually break, the moisture will eventually surge, the pattern will eventually transition, and when it does, the people and the systems that have maintained their awareness and their preparation through the long weeks of the forecast collapse will be best positioned to navigate what comes next, not with false certainty, but with the grounded, data-informed, appropriately humble awareness that the current situation demands. Watch the atmosphere, not the model output. Understand what the pattern is doing right now, today, not what the models projected 2 weeks ago that it would be doing. And be ready for the transition when it comes, because when a blocked August finally gives way, it does not give way quietly. It gives way with everything the atmosphere has been holding back, all at once, on a landscape that is least prepared to receive it. That transition is coming. How soon and how dramatically, no forecast can tell you with certainty. What the data and the physics can tell you is that it is real, it is inevitable, and when it arrives, it will be one of the most consequential weather transitions this part of the country has seen in years. Be ahead of it, because the one thing the collapsed August forecast has made undeniably clear is that being behind the atmosphere is always more expensive, more dangerous, and more damaging than being ahead of it. The forecast collapsed, the heat stayed. And now what comes next? Whatever the models say, whatever the timeline proves to be, demands the most serious and the most clear-eyed attention that the people in its path can bring to it. The atmosphere has earned that attention. Give it. There's another dimension to what happens next that has not yet been addressed, and it is the one that connects this specific August forecast collapse to the broader story of how extreme atmospheric patterns interact with the infrastructure and institutions of the regions they affect. Because what the collapse of the August forecast has revealed is not just a limitation of the models. It has revealed a limitation in the way that forecast information is communicated, received, and acted upon by the systems and the people who depend on it. The relationship between weather forecasting and decision-making is one of the most studied and least understood problems in applied meteorology. Decades of research have shown consistently that the simple provision of accurate forecast information does not automatically translate into optimal decision-making by the people who receive it. Human beings process probabilistic information poorly. We tend to interpret a forecast showing a 70% chance of pattern change as essentially a certainty that the pattern will change, rather than as a statement that 30% of the atmospheric possibilities consistent with the current state of the atmosphere involve no pattern change at all. We anchor strongly to the most likely outcome and discount the tail possibilities, even when those tail possibilities carry enormous consequences if they materialize. And we update our mental models of the situation slowly and reluctantly when the forecast evidence accumulates that those models are wrong. The August forecast collapse is a case study in all of these human factors. The pattern change that the models were showing 3 weeks ago was a probability statement, not a certainty. Embedded in the model ensemble was significant spread, significant uncertainty, about the timing and magnitude of the projected change. But the communication of that uncertainty and the reception of it by the people and institutions making decisions based on the forecast was filtered through the human cognitive tendencies that consistently lead us to underweight uncertainty and overweight the most likely modeled outcome. The relief that was projected became, in the public consciousness and in the planning of institutions, an expectation rather than a possibility. And when the expectation failed to verify, the damage was not just meteorological, it was institutional, economic, and in some cases directly harmful to the health and safety of people who had moderated their protective behaviors on the basis of a forecast that proved wrong. What does this mean for how we should process what the models are showing us now about what happens next? It means we should read the current forecast with the specific and explicit awareness that the same model systems that failed to anticipate the persistence of the current blocking pattern may be similarly miscalibrated about the timing and character of the eventual pattern transition. When the models now show a significant pattern change in the extended range, as they are beginning to show for the latter part of August and into September, the appropriate response is not to update our planning around that projected change as a certainty. It is to hold it as one of several possible scenarios, weighted appropriately by the confidence we have in the models given their recent performance, and to maintain the preparations and the awareness that the current extreme conditions warrant, regardless of what the extended models are showing. This is harder than it sounds. The psychological pull of the favorable forecast, after weeks of unrelenting heat and drought, is powerful. When the models show relief on the horizon, people want to believe it. The desire for the extended forecast to be right is itself a source of bias in how it is received and acted upon. Maintaining disciplined uncertainty about forecast outcomes that look favorable requires a kind of cognitive effort that is unnatural and that runs against the grain of how human beings process information about the future. But it is exactly what the August forecast collapse demands of us, because the cost of again allowing hopeful forecast expectations to drive down the vigilance and the preparation that the situation requires is too high to pay twice. The specific elements of what the models are now showing for the pattern transition deserve careful examination because they are not uniformly encouraging, and the details matter enormously for what actually happens next in different parts of the country. For California, the models are showing an interesting and complex evolution. The ridge that has dominated the west is expected to eventually shift its position eastward, which would bring California into a more progressive atmospheric pattern where Pacific systems can approach and make landfall more readily. But the timing of that shift remains uncertain, and the character of the systems that would follow, whether they are the kind of organized atmospheric rivers that deliver widespread beneficial rainfall, or the kind of localized intense convective events that dump rainfall too quickly to be absorbed and too specifically to provide widespread benefit, is not well constrained in the current model output. California needs the former and is vulnerable to the latter, and the difference between them in the current atmospheric context is the difference between relief and an additional disaster. For Texas, the model guidance for the pattern transition period shows a scenario that will be familiar to anyone who has lived through the volatile shoulder seasons that define Texas weather in late summer and early fall. The transition from the blocked, hot, dry pattern to the more progressive, energetic pattern of fall does not happen smoothly in Texas. It happens in a series of dramatic events. Strong, cold front passages that crash temperatures by 30 or 40 degrees in a matter of hours, that bring lines of severe thunderstorms along the frontal boundary, that dump rainfall in amounts that overwhelm the drought-cracked soil and turn dry creek beds into raging torrents within minutes. These frontal passages are not simply relief. They are weather events in their own right, capable of producing significant damage and danger even as they end the heat that has been the dominant story. The severe weather risk associated with the first major cold front passages into Texas following the collapse of the blocking pattern is something that deserves specific emphasis, because the public communication of weather events tends to frame the end of the heat as unambiguously positive news. And, in the long-term sense, it is. But the transition itself, the meteorological mechanism by which the heat ends, is not benign. The clash between the Arctic air that the first major fronts deliver and the deeply warm, deeply moist atmospheric environment that the heat dome has created produces temperature and moisture gradients of extraordinary magnitude, gradients that are the raw material of severe thunderstorms, large hail, damaging winds, and tornadoes. The very conditions that make the transition out of the heat dome so dramatic are also the conditions that make it dangerous. The Gulf Coast faces its own transition risk that is distinct from the inland severe weather threat, but equally serious. As the atmospheric pattern evolves and the blocking ridge migrates, the steering currents for tropical systems in the Gulf and the Caribbean will change in ways that could bring one or more systems into a more direct threat position for the coast. The transition period from a blocked to a progressive atmospheric pattern is often associated with increased tropical activity in the Gulf, because the reorganizing jet stream creates windows of reduced wind shear that allow Gulf systems to intensify more effectively. Combined with the warm Gulf waters that are still very much present and available as fuel, the first weeks of the pattern transition could represent the peak tropical threat period for the Gulf Coast this season. The Southeast faces the transition in the context of its own specific vulnerabilities. The rivers across the Carolinas, Georgia, Alabama, and Mississippi are running low after the drought-suppressed summer. When the first major rainfall events of the pattern transition arrive, they will hit watersheds whose soils are severely depleted of moisture, which might suggest good absorption capacity, but which in practice often means the opposite, because drought-hardened soils with disrupted surface structure and reduced organic matter content absorb rainfall less efficiently than moist, well-structured soils. The flash flood risk across the Southeast during the transition period is real and deserves the kind of specific public warning and emergency management preparation that it may not currently be receiving given the focus on the heat event itself. What comes after the transition, the fall and winter weather that follows the collapse of the August forecast and the eventual reorganization of the atmospheric circulation around the El Niño pattern, is itself a subject of significant forecast uncertainty. The El Niño that is building in the Pacific will increasingly dominate the atmospheric circulation as autumn advances, superimposing its specific pattern of enhanced subtropical jet stream and increased southern storm track on whatever residual patterns remain from the summer's blocking configuration. The resulting fall and winter weather, as we have discussed in other contexts, carries elevated risks of its own for severe thunderstorms across the south, for significant precipitation events along the entire Gulf Coast, for winter weather extremes in Texas and the southern plains, and for continued atmospheric river activity in California. The collapsed August forecast is not the end of the story. It is a chapter break. A moment when the narrative that the models were telling us about this summer has been overtaken by the narrative that the actual atmosphere is writing, and when the implications of that real narrative for what comes next are being clarified in ways that the earlier forecast projections obscured. The real narrative is harder than the forecast narrative. The heat is more persistent. The drought is deeper. The transition, when it comes, will be more dramatic, and the fall and winter that follow will be shaped by the full weight of the El Niño pattern operating on a landscape and a set of human systems that have been stressed by an August that collapsed the expectations that had been built around what this month was supposed to deliver. Understanding what actually happens next requires letting go of the forecast that did not verify and engaging honestly with the data that is actually in front of us. The atmosphere does not owe us the relief that the models projected. It operates according to its own physics, on its own schedule, with its own agenda. What that agenda looks like right now is a continued blocking pattern in the near term, a significant pattern transition when the blocking finally breaks, and a fall and winter dominated by the El Niño signal that will write its own chapter of this extraordinary year in the weather records of California, Texas, and the South. That is what actually happens next, not the August relief that the forecast promised and that did not come, but something more complex, more consequential, and more demanding of the vigilance and the preparation that the people in the path of it can bring to bear. The forecast collapsed. The atmosphere did not. And the atmosphere, as always, will have the final word. Watch it, respect it, and be ready for whatever it delivers next. Because after an August like this one, the atmosphere is not going to settle quietly into autumn. It is going to arrive.